Hello everyone, my name is Jinsun, and today I'm going to provide a demo of using the NS3 network backend with the ASTRA-sim simulator. This supplementary video has been built on ASTRA-sim's version on the Micro 2024 tutorial. While we did not add any significant features, there have been some bug fixes that were added to the ASTRA-sim repository. I will discuss how to reflect these bug fixes in the repository for those who have already cloned and went through the demo in Micro 2024. Now, to begin with, we have discussed in Micro 2024 that ASTRA-sim's strongest feature is its modularity. In other words, we are able to choose between different network backends in a plug-and-play manner, depending on the need for the fidelity. Natively, ASTRA-sim supports two network backends, what we call the analytical backend and the NS3 backend. Users are able to add different network backends that they implement depending on their own needs. But if we look at these two network backends for now, the analytical backend is able to provide results fairly quickly at the cost of fidelity, whereas the NS3 backend, being a packet-level simulator, is able to provide results with a much higher fidelity at the cost of a rather long wall clock time to simulate specific workflows. To go into a bit more detail, what we call the NS3 backend has been built upon artifacts of past research, focusing on RDMA congestion control in a data center setting. We took that artifact and modified it so that it could simulate RDMA traffic between GPUs in a realistic data center network, and so that it would be able to handle events simulated by the ASTRA-sim simulator. Now, in general, the repositories and the inputs has not changed since the Micro 2024 tutorial. However, as I've mentioned, there have been some bug fixes, which is why we strongly urge folks to check the commit of the tutorial repo to make sure that this is the most current. Once this has been verified, users will be able to clone the most relevant version of the ASTRA-sim simulator. Now, for the sake of time, I've already cloned the repository, which is why I'll go straight into launching the Docker container. Oh, and also, do note that I'm going to skip some of the parts that have already been discussed in the demo video, in the original demo, which is why for like some logistics stuff like getting the Docker container or some installation script, do look at the original video, which provides more information. Anyways, let's go ahead and launch the Docker container. Again, I'll skip installing the Chakra package. So for engineering reasons, in ASTRA-sim, the main function follows the network backend. What this means is that if we have different network backends, we're going to have different compile scripts and also different binaries that are used to run the simulator, which is why here we're going to run the compile ASTRA-sim NS3 script to build the ASTRA-sim simulator. Okay, now that we've finished compiling, we can see that the binary for the NS3 backend is different from the binary for the analytical backend. Now that we have a built version of the simulator, let's go ahead and run a sample workload. So while this is running, I would like to point on some points. So if you look at the demo script, you will see that some flags, for example, the workload configuration or the system configuration, is similar or identical to what we saw with the analytical backend. Whereas in the case of the network configuration, we see that it's pointing to a completely new file. And in the case of the logical topology, we see that this is a completely new flag that's been added. We see that here we have a completely new flag, and the network configuration is pointing to a new file at the new directory. So for now, let's have a look at what this configuration file is. If we look into this file, we can see there are several knobs. This file, or to be precise, this format, is what the NS3 backend accepts to configure several aspects of the simulated network. And for the sake of simplicity, I won't go into explaining all of these fields. There's a description for them in our wiki and our documentation. But for now, let's have a look at this topology file flag. You can see that this topology file flag is pointing to another file. And then one might ask, we've seen the logical topology configuration file over here, and this is different. So how is this logical topology configuration different from that topology field we saw in the text file? Here, let us go back to the concept of the logical topology versus a physical topology. The physical topology is literally the topology that describes how um, GPUs are connected with actual wires or actual like physical switches. Right? So for example, we could discuss like a switch topology or a fat tree topology. Whereas the logical topology is, well, literally logical, right? It governs um, what GPU talks with what GPU, like whether GPU 0 will talk with GPU 1 or whether it will talk with GPU 16, right? So for one very simple example, assume we have a scenario where there are 128 GPUs in a fat tree topology. We could have a big ring logical topology, a single logical ring where GPU 0 talks to GPU 1, GPU 1 talks to GPU 2, all the way until GPU 126 talks to GPU 127. Right? That logical ring, while the logical topology is a ring, the actual physical connectivity is defined in the fat tree class topology. So that's how the logical topology could differ from a physical topology. And what you see in these slides are examples of how these logical topology and the physical topology are defined in the ASTRA-sim configuration. First, on the logical topology are some examples on how you can define the logical topology and the physical topology. So in the case of the logical topology, what you see are two different examples, where the first example is you have a single big ring that connects all 128 GPUs at once. So what we see here is that you have a single number 128 that shows that because this is a single element of the array, you only have one dimension, which consists of 128 nodes. On the other hand, if you define a logical dimension that looks like this, where you have two different elements, it shows that you're going to have a two-dimensional logical topology, where the first dimension consists of 8 GPUs and the second dimension consists of 16 GPUs. This kind of communication could work better in a case where, let's say you have, like in an A100 or an H100 machine, you have 8 GPUs that use intra-node communication, whereas after that intra-node communication, you have 16 inter-node communications across 16 GPUs, across 16 different nodes. This kind of defines such a scenario. On the right side, you see how we define the physical topology. So remember, this configuration file that we've seen before is something that the NS3 simulator understands to um, to define the topology of each of the RDMA components. The NS3 simulator itself does not understand the logical topology. That logical topology is something that the system layer is going to use to break down collectives into send and receive messages. So the NS3 simulation, the NS3 backend will take the network configuration file, and amongst all of the other knobs that we've seen, we see the knob that points to the physical topology file, which defines um, the physical connectivity of the network. Now, I will come back to the physical topology a bit later, but for now, let's look at this point where, in the case of the analytical backend, the logical topology is automatically assumed to follow the physical topology, whereas in the case of the NS3 backend, we're able to decouple the logical topology from the physical topology. What this means is that we are able to test a range of logical topologies that correspond to the physical topology. So what this means, let's just see how it works with another demo. This demo is if you look at the workload information later on, you'll see that is the same workload information. You have the same single all reduced communication that is carried out across 128 nodes with the same physical connectivity. And the only difference here is that in this case, we use a two-dimensional ring instead of a one-dimensional ring. And because we're using a two-dimensional ring, we have to define a logical topology um, that shows two dimensions, as I've shown before. But one thing to also note is that if you look at the input, you can see that we're using a ring system.json instead of ring sys.json in the first demo. What this means is if you look at the system, you can see that we're telling the system layer to use two-dimensional rings through the system layer input. And through the logical topology configuration, we're telling the system layer that, hey, we want this number of nodes for the first dimension and this number of nodes for the second dimension. Because although it seems counterintuitive, we are able to simulate scenarios where even within the same two-dimensional rings, we're able to simulate scenarios where, let's say, for example, the first dimension consists of 32 GPUs, which is unlikely, but still possible. So one thing to note over here is that the dimensions, the number of elements in the system configuration must match the number of elements in the logical topology so that the system layer is able to understand that this is a two-dimensional collective communication that's going on. And again, note that the actual network configuration itself has not changed, right? So let's go back to defining the physical topology. So if we open the network file, we can see that it's pointing to this specific topology file, which is actually the physical topology file. So if we open that physical topology file, this is what we have. What we see on the screen is a bit of a simplified version, but this is the full version. So here what we're going to do is we're going to define a a factory class topology where you have top of the rack switches and then spine switches on top of the rack switches. And each of the top of the rack switches contain 16 GPUs in the top of the in each rack. So slightly rephrasing, what we have is we're going to have 128 GPUs, But because there are 16 GPUs per rack, there's going to be 8 top of the rack switches, and similarly 8 spine switches, which provides cross connectivity. So if we look at the text file that defines the physical topology, uh, it starts with the first line starts with 3 numbers. The first number is the number of switch plus the number of GPUs. This um, within the low layer implementation of the NS3 backend is um, what the NS3 backend calls like the number of RDMA drivers. So the number of participants in the RDMA communication. But high level, this is just the number of GPUs plus the number of switches. Over here, you have just the number of switches, and over here, you have the number of links. So the NS3 backend will use this to be able to parse the whole file uh, that comes below. So over here, you have a list of the indexes of the switches, right? So what this means is that um, ID 128 to ID 143 are switches, and in other words, ID 0 to 127 are going to be um, GPUs that participate in the RDMA traffic. So here, what follows that is one line corresponds to a physical link. So the first two elements are the indexes of the participants that the link connects. This is the bandwidth, this is the latency, and this is the packet drop rate, the error rate, or the rate at which packets fail to communicate using these links. So if you see, you have the connections between the first 16 GPUs and their top of the rack switch 138, and then you have the connection between the next 16 GPUs and their own top of the rack switches. And after all of this, you can see that, and here we have the connections between the top of the rack switches and the spine switches above them. This is an arbitrary scenario where we simulate using the same bandwidth with a larger latency, but depending on what the actual physical connectivity looks like, the users are able to um, modify these numbers as they wish, and users are able to write their own script that generates these physical topology files. Now, using this, you're able to create arbitrary physical topology. So, for example, you're able to create a arbitrary topology where you have 8 GPUs that are connected with a single switch. So again, 9 is the number of GPUs plus the number of switches. You have a single switch that is connected with 8 links. So on the second line, you have the ID of the switch, and following is the 8 links that connect each of the GPUs to that single switch. So again, as a final demo, let us see what happens if we run a demo with this simpler physical topology. So note here that we are using a new configuration file that points to the much simpler physical topology. We have a logical topology which only defines a single logical topology. We only have a system layer that defines a single dimension of a ring. So this concludes the NS3 demo. Again, to briefly recap, what we have seen is that we were able to simulate different workloads using different physical topologies and also a different logical topologies, that is, different dimensions of collectives. Um, so yes, uh, as it is with other network backends, there are more documentations available on our public wiki. If you have any questions, please feel free to reach out to the ASTRA-sim users email mailing list. That way, in general, users are able to get the best responses with that general mailing list. Thank you for listening through this demo. Please feel free to reach out if you have any questions.